Hello everybody. So today what we are going to do is we are going to start with a topic of fluid mechanics, and in fluid mechanics this Newton's law of viscosity is what we are going to discuss. So Newton's laws of viscosity is a very important concept. If we want to study viscosity, if we want to understand the concept of viscosity and what does it mean for our entire perspective journey of the fluid mechanics, it is very important. So in terms of this, what we have now is a fluid. So let's say we are given with a fluid. It has various different layers, as you can see. So there are different layers of the fluid present over here. And now what we do have, let's say we are going to apply a shear stress on this. The shear stress is tau. So tau is the amount of shear stress. Now what shear stress means? Any force is shear force if it is applied parallel or tangential to the surface. Let's say for example, I have a box like this, right? And if I have a box like this is solid, let's say. And if I do like this, then what will happen? It will deform in this fashion, in this manner, such that it will move along this line. So the force applied, as you can see, is like this manner. So that means it is tangential to the surface. So whenever we are applying the force tangential to the surface is known as shear force, and this shear force per unit surface area is known as shear stress. This itself is known as shear stress. So what happens if we apply shear stress to a fluid? So first of all, fluid does not have any memory. So it means that the fluid will keep on going like this. It means it will keep on deforming. So its deformation goes on and on and on. It has a continuous deformation. So what I am saying is it has continuous deformation. That is what happening over here. Continuous deformation of the fluid. Now if it is undergoing continuous deformation, it means what? See, it means this. Continuously it is deforming. Now what we are going to do is, let's understand it in this fashion. I am going to draw the velocity profile. Why velocity profile? See, when you are in touch or in contact with this uppermost layer, so this uppermost layer you are like applying shear force, so it tends to move with you, right, because of the touch, because of the contact. So it tends to move in this direction only. And now if I draw the velocity profile, it goes something like this. Okay, so the outermost layer has the maximum velocity, and then the inner layers have a velocity which is lower than the outermost one, and finally we have this layer having a velocity 0. Means the entire layer present over here, let me show it with a separate color like this. So this entire layer has a 0 velocity, and hence it is known as no slip layer. This layer is known as no slip layer. It has no slipping taking place. So this is a no slip layer. Okay, this is a no slip layer. On this layer there is no slipping taking place. No slip means over here relative velocity is 0. What means relative velocity? Relative velocity means the velocity difference between the fluid and the no slip layer. So the relative velocity between them is 0, entirely 0. Okay, so whatever be the velocity of the fluid, let's say fluid layer over this plate over here, the same will be happening. For example, I'll explain it to you in a more vivid manner. Let's say you have a surface, and now what you do is you have spilled water on this. So water has been spilled like this. Okay, so if I am keeping this plate as a stationary, this water layer will be also stationary. But if I am moving it with the velocity u, this water layer also moves with the velocity u. So that means there is no relative motion between these two. the relative motion, the relative velocity between these two is 0. That's what I am saying. This is what I am trying to explain it to you. Fine. Now, so having this thing in mind, what we have obtained up till now is a velocity profile. So this being our velocity profile. Let me show it to you. Yeah. So this, my dear students, is our velocity profile, like this. All right. So what I am going to do is, I am going to do the analysis. So analysis is like this. At a distance y from the base, we have a thickness of dy. This plate has a thickness, these layers are at a distance dy apart. So if I am drawing it, it will be like this. What I am doing is, this one is zoomed. I have taken this layer and I have zoomed it up. Why I have zoomed it? To show you a better perspective, to show you a better diagram. So I am saying the velocity over here of this layer is u, and this is dy. So the change in velocity will be du. I can say with the help of geometry is that this is u, this is also going to be u. So the change is this much, du, right? So the velocity of this layer shall be u plus du, all right? And the angle over here is theta. This is what I am saying. The angle over here is theta. So if I am trying to say tan theta, if I am going to say tan theta, right? Or since the angle is very small, I am saying d theta. Not even theta, I am saying d theta, because the angle is very small, right? Angle being very small, that's why I am bound to say this is d theta. So tan d theta will be this distance du. Now this has to be a distance, but du is only speed, so I have to multiply it with the time dt, and this is the base, which is dy. So what is dt now? If I try to explain dt to you, dt will be the time period. All right, dt is the time period in which the change is happening. Now about the change, why changes are happening? See, there is a cohesive force between the layers of the fluid. See, these are the fluid molecules, let's say. For example, these are the fluid molecules, like this. Now what happens is, there is a cohesion force between these molecules, and because of this cohesion force, when you are pulling the uppermost layer forward, these get stretched out, and hence they ask these molecules in the bottom layer, they ask these upper molecules to not move forward, and hence a resistance is observed. So this is very simple. For example, you are holding hands with your friend, some other person is pulling you, so your friend won't let you go. So if the friend won't let you go, that means he or she is asking you to stay. And what does this mean, asking to stay? It simply means that the force applied is being offered a resistance backward. So the velocity of this layer will automatically be less than this layer. So let's say this is u, this is v, so v will be greater than u. Okay, so the velocity of the bottom layer will be automatically, hence there is a decrement in the velocity of the layers. Okay, so this is the time period in which this change is taking place, right? So now if d theta is very small, see, the changes are very small. Why? Because if you apply, you are taking very small, there is a very small gap dy. So the layers are very close to each other. Since the layers are very close to each other, hence d theta is very, very small. So while this d theta is very small, it simply means that tan d theta will tend to d theta. So I can say d theta is equal to du dt over dy, which means d theta over dt equals to du over dy, right? And this d theta upon dt, d theta by dt is known as rate of shear strain. This is known as what? Rate of shear strain. We define it in this fashion, we define it in this manner. It is the rate of shear strain rate, sometimes it is also known as this. So, what does this mean? It simply means at what rate the fluid is being deformed continuously. So, what is the rate of fluid being deformed continuously is rate of shear strain, alright. Fantastic. So, what does Newton, what is the observation of Newton which he told? So, Newton simply observed, observation, Newton, Sir Isaac Newton, he simply observed that the shear stress applied across the surface of a fluid or the fluid surface, the surface of a fluid, this is the observation, shear stress applied across the surface of a fluid is simply, you can observe it, this shear stress which is being applied on the surface of the fluid is directly proportional to the rate of shear strain. So, it is directly proportional to it, rate of shear strain. So, what does it mean? It simply means whatever be the layer of the fluid, if you are applying shear stress and let us say you have applied more shear stress, there will be more deformation. Simple. Tau is proportional to d theta over dt. And since, see, can't you see that measuring this is very difficult? If you want to measure theta within the fluid layers, it is very difficult to do so. So, what is to be done instead? We can use the previously derived mathematical relation like du over dy. Why? Because d theta over dt is du by dy ka proportional. Okay, and du by dy is simply velocity gradient. It is nothing but velocity gradient, right? It is velocity gradient, and coincidentally, since it is equal to the rate of shear strain, hence we can substitute this over here. We can substitute it over there. Now, this tau becomes mu times du over dy. Now, what is this mu? Mu over here is being used as a coefficient of viscosity. I mean, it is being described as a coefficient of viscosity. It is the definition of it, and we will go into this a bit later. But for a while, this is being used as proportionality constant. It is being used as a proportionality constant. And this itself is also known as the coefficient of viscosity. Coefficient of viscosity or simply dynamic viscosity as well. Dynamic viscosity. So, viscosity, dynamic viscosity or even absolute viscosity, it is known as in this manner, because once we move forward, we will also come across kinematic viscosity, which is another form of viscosity, but its formula is different, right? So, what we have obtained up till now is tau equals mu du over dy, right? This is the Newton's law of viscosity formulation. So, from here we can define a new term which is mu equals tau over du over dy. Now, what is the unit first of all? So, let us talk about the units. See, its unit is Pascal, because Newton per meter square Pascal, and its unit is meter per second, and into this is dy is in meters, cancel. So, this becomes Pascal second. This is the SI unit of coefficient of viscosity. Also, if we see it in a bit depth, Pascal second can also be written as Newton per meter square into second, which can be further written down as Newton is kg meter per second square, and this is meter square and this is second. So, 1 goes out. So, what we have instead is kg per meter second. So, now what we can say is meter mass is m1 L minus 1 T minus 1. This is also a formulation, m minus 1 L minus 1 T minus 1, right? Okay, fine, fantastic. So, this is dynamic viscosity or absolute viscosity. This is how we define it. And also if I want to describe it, it can be written as, let's say, tau upon 1. If du by dy equals to unity, then mu equals tau, which means dynamic viscosity or the coefficient of viscosity, dynamic viscosity is the amount of, it is nothing but the amount of shear stress required in order to, shear stress which is required in order to, dynamic viscosity is the amount of shear stress which is required in order to do what? See, it is required in order to produce a unity velocity gradient, means a velocity gradient of magnitude 1. So, this is what we say about it, right? Okay. So, tau equals mu du over dy. Now, if let's say you have been given with the velocity profile, if u as a function of y given, then differentiate u with respect to y and find shear stress at any given location. It is as simple as that. One more factor what I want to emphasize over here is linearization. See, this is a concept which is done, and this is basically an approximation concept, linearization of Newton's law of viscosity. Now, what is this linearization principle? So, let me explain it to you. If we talk about this linearization principle of Newton's law of viscosity, see, you have drawn a velocity gradient like this. There is a, let's say, a velocity gradient over here. And let's suppose when we talk at extremely lower points, or when we talk about the points which are at very near, right, which are very near to the surface. So, let's talk about these points, right, let's talk about these points. So, till here what I can emphasize is velocity profile is somewhat linear, can be approximated as linear. So, we can approximate this velocity profile as linear. It can be approximated as linear. From here you can see the curve, but till here you can say that this is linear. So, this is linearization of, although it may be that it is not actually linear, but yeah, we can approximate it because the tangent going from there is a straight line. Let's say this height is h and the velocity over here is v. So, we can simply write tau equals mu v by h. This is the linearization. And if in questions, in problems given to you, it is not mentioned as to what is the velocity profile, you can simply do the linearization trick. Means simple, take the outermost velocity, divide it with the gap, multiply it with mu, you will get to know tau. or shear stress in Pascal. One additional thing I want to emphasize on this is unit of viscosity. See, in terms of unit of viscosity, mu has an SI unit of Pascal second. This is an SI unit. It also has a CGS unit, and this CGS unit is poise, right? So let's talk about this CGS unit. 1 poise shall be equal to 1 gram, because it was kg per meter second, so it will be 1 gram per centimeter second. 1 gram is 10 to the power minus 3 kg, right? This is 10 to the power minus 2 meter, and second is second, so there won't be any change. This will go like in the numerator minus 3 into 10 to the power 2, it will become kg per meter second. This kg per meter second is Pascal second. So now what I am going to do is, this 1 poise is 10 to the power minus 1 Pascal second. So if the units are mentioned in poise, then you can convert it into Pascal second. For example, let's say we have 20 poise, a value of mu, then it will be 2 Pascal second in SI unit, right? So the conversion goes like this. Also, you can take one more example, like if mu is given as 10 to the power 3 centipoise. So 10 to the power 3, centi means 10 to the power minus 2. Wherever centi is there, you can do this, and it will 10 to the power minus, it means 1 Pascal second. So this also you can do. So these are the basic conversions. So I hope Newton's law of viscosity is very much understood to you, and we have discussed each and every aspect of it. We have also discussed about the fluid and everything. So this, my dear students, is Newton's law of viscosity. It introduces us to a new concept, a new property of the fluid altogether, which is known as dynamic viscosity or coefficient of viscosity, or we can also simply say viscosity, whose definition I have discussed, whose units and dimensions also I have discussed, and the conversion to various different units has also been discussed. So this is a very important topic which has been covered, and I hope you have understood it.